factorization, some may say, oh, it's just a math skill I've learned in elementary. Though I know some of you have not mastered this skill yet, but anyways, factorization is way more crucial than that in our daily life. It's actually a padlock on your bank account, chat message, and most importantly, browsing history. But how? How can factorizing a prime number help with that? Now, imagine you're sending a love letter to your crush, who I feel sorry for. To prevent anyone else from intervening and reading your embarrassing love words, you need to encrypt it with some complex process, which the clever audience must have figured out: prime factorization. To refresh your mind, a prime number is an integer greater than 1 with just two factors, 1 and itself. If we take two such prime numbers, multiply them into n, show n to everyone, but let only people knowing the prime factors gain access to the message, then we've done the encryption. Now, the question arises, can this really prevent others from seeing your message? Let us see this from some basic modular arithmetic. First, focus on the multiples of 5 between 0 and 20. Then, look at the other ones that give a remainder of 1 when divided by 5. We say A is equivalent to B modulo 5 if A and B have the same remainder when divided by 5. Let's try to factorize a small number. Take 15 as an example. What we'll do is to find a division that gives a remainder of 0. Try with each factor. Easy to tackle, right? Thus, we found the prime factors of 15 through brute force. Well, what if the number is larger? Let's say 10,007. Interesting. After decades of attempts, we still couldn't find its factors. Well, to read your love letter and see what a clown you are, there must be some smarter ways. We know the fact that at least one factor of n is smaller than the square root of n. Just think about it. This narrows down our guess range. Still, even if all classical computers on Earth try to factorize a 600-digit number, it would take the time longer than the age of the universe. But for quantum computers, things become much faster if we apply some tricks. So, what are the other smarter ways? Here, let me introduce you Shor's algorithm. But before that, let's establish some non-facts that make things easier. First, we assume n to be odd, because we know 2 is a factor of any even number. Second, we know our guesses lie between 1 and n. Let our guess be an arbitrary number a between 1 and n, and g be the greatest common divisor of a and n. If g is greater than 1, then we know it is a factor of n, otherwise not. If we keep multiplying a by itself, then eventually some power of a divided by n gives a remainder of 1. then a to the power of r is equivalent to 1 modulo n. In case r is an even number, then we can perform some mathematical operations to quickly find the factor of n. This is called Euclid algorithm. However, the attempt fails if the power is odd. But still, after trying multiple different a's, the success chance increases to nearly 100%. Next, let's see how computers find such a to the power of r equivalent to 1 modulo n. A classical computer computes a to the power of r one by one. For a large number, this process is time-consuming. But a quantum computer can do this much faster as long as we apply a smarter algorithm. In contrast, using quantum superposition, a quantum computer can compute all the outputs at once, making the computation much more efficient. And magically, when measuring it, we only get one output of the most probability. You may wonder how. Well, at the beginning, all the outputs have the same probability. But what if we can find a way to boost the probability of one of them? This can be accomplished through interference, similar to wave interference in physics. Notice there is a similar periodic pattern among the solutions of R. As you have seen, among all measurement results, some good pairs repeat with a period of R. By finding the frequency of these good pairs, we can deduce R. To obtain such frequencies, we need to perform quantum Fourier transform, a process in which things we don't want cancel out, leaving the frequencies. Similarly to wave interference. Thus, we obtain R decrypting the factors of a large number. By now, we have shown how a quantum computer can break your padlock and see your deepest hidden secret. Here's a summary for Shor's algorithm.